I was here during second holiday.
All right, we are now recording, so we do not want to talk about Cody Masters being tardy. All right. So, wait, whoops.
Mr. Clark, maybe you should get more sleep. You're letting things.
I've let things slip. All right, sample 2, number 43. Now, this was one. Would this be a good one to do?
Sure. Yes, I guess.
Did anybody get the right answer without help and tell me what you did?
I just set up an integral.
You did. Nicely done.
What was the?
Okay. Set up an integral. Now, did you set up an integral because you thought, well, this is one of the new ones that we now should know how to do, and since the newest thing we learned was integrals, so I'll bet there's an integral? Kinda? I mean, was that what you were thinking, or?
Kind of, well, like they give me the rate of change that the gallons were coming in,
Okay.
and then they give me, they want to know how many gallons of oil are coming in. So it, I don't know, that just sends area to me. So I thought,
Well, when we first did area, we talked about miles per hour, and the area was miles, so gallons per hour, gallons.
Yeah, that was pretty much what I was going to say. Just thinking about the units.
The units, because if you think of gallons as V, let's say, and then this integral here, this is V prime, and then of course yesterday I did give you that thing on the board where I give you the integral of F prime, kind of a situation. So if you think of this as V prime, it kind of makes sense that the integral of V prime would be V, right? Gallons, okay? And that's true. Now, I think, even without that little hint that I gave you, to me, this is a problem that right now would have been kind of a challenging one to do. By the time we get to the AP test, by the time we get to the finals, to me, this will be a very easy one because of all of the work we'll do between now and then. So a lot of these things in the packets right now, these additional problems we're doing, like on the 2012 free response, they're going to stretch you a little bit in your thinking of what we know, but I think you have that information. It's just kind of putting it together now. And then, of course, my hope over the next, month and a half, 2 months, whatever, as we get towards the finals, is that we will, we'll learn some new things along the way, but also that we'll really be putting all this stuff together. And it'll really make sense. And I think that's what's happened typically in the past. And it's, and I feel good about where we're at for that happening again as well. So let's talk, because there's several things going on here. Did anybody else do this without an integral? Now, when you say integral, you mean like this kind of thing. Okay. I mean, that's what an integral is. But did anybody do it without that? I mean,
And get the right answer.
what's that?
You get 600 if you don't get
As far as just plug in a 4? Yeah, because that, if you plug in a 4, that would just be gallons per hour. So that'd be the rate that it's coming in at that time. Right. Now, what about, I guess what I was thinking was this. You could not think area or integral.
I assume, like, you have the rate, so you have 600 gallons in 4 hours. I mean, 600 gallons per hour for 4 hours, sort of.
Sort
Am I
of.
saying this right?
The only problem is that's the rate at 4, but it's not the rate for the entire 4. Because when T's a 1, the rate would only be 300, right? So what you have is, this is going in faster and faster as time goes on. And so what's happening is, well, you could probably say, well, that'd be too much then, because if it was 600 the whole time, it'd be this much, but it's not 600 the whole time, so that's too much, and you could kind of eliminate some things. But we'll be able to do way better than that. So we wouldn't do that. Now, but here's what I was thinking. What I was thinking is, if you called this V prime, I mean, let's think about it. If this is V prime, 300 T to the 1/2, but we want an answer of gallons, which is V, how could you go from V prime to V? Anti-derivative. Now, to me, that's different than integral. They're connected, but they're two different things, right? An antiderivative is one way of doing an integral. It's one way of doing an integral, but so they're two kind of different things, all right? But they'll get us to the same place here. So you could have done this with, and I want to talk about both because they're both important. So one way of thinking would be, okay, I got gallons per hour, which I'll call that V prime, and I want to get to V. Well, I do antiderivative. So I'll raise this up to 3/2, so I got 300 T to the 3/2, divide by 3/2, that'd be what? Times by 2/3. So that would cancel that, that'd be 100. So I would have 200 T to the 3/2. Now, can I plug in a 4? So I put in a 4. That would be square root, which is 2. 2 cubed is 8. 8 times 200, 1,600. And I believe that's the right answer. Now, there's something we kind of left out of that. The plus C. But it actually doesn't hurt us that we left it out in this case. Why? Read through the problem. Logan? Okay. Remember, your plus C is based on your initial condition. In this case, since the tank is originally empty, we know that the volume at time 0 is 0. It's our initial condition. So this is really like an initial value problem. Really, it's like a differential equation. We have a derivative, or differential equation. We have an initial condition. What I should have done, I was waiting for somebody to say it. I kind of went through it real quick so to see if nobody would. But anyway, I was waiting for somebody when I did the antiderivative to say plus C, plus C, plus C. Put on a plus C there, but then you put a 0 in, right? Because let's talk about this, man. This is really important. So let's forget the plus C a minute. So we get the 1,600 gallons. The question said, how many gallons are there after 4 hours? We said 1,600, but that was only right because it started with 0. What if there would have been 100 there to start? Then the answer to the question would have been 1,700. So now, very important, what does this 1,600 represent then? When we forget the plus C, what's the 1,600 represent? The change in the gallons. Now, this is going to be a really important thing. I'm going to emphasize it a lot. We'll talk a lot about. This is the first time you're hearing this. That this antiderivative without the plus C is really the change in gallons. Now, think of the terminology then. When we were talking about derivative, we talk about the rate that something was changing. When we do the antiderivative, we're talking about the amount that something changes. That's what antiderivative and also integral gives us. So this 1,600 is the amount that the water changed, the volume, over those 4 hours. The plus C says, but you also have to consider what there was to start with. Okay? So if the question would have been how much water came in those 4 hours, 1,600. The plus C wouldn't matter. But if the question is how many gallons are in the tank after those 4 hours, then we have to consider the plus C. Okay? Now, let's talk about it from an integral standpoint. From an integral standpoint, did you guys set it up as 0 to 4? Okay? And you do 300 T to the 1/2 dt. And again, this is gallons per hour in here. And so this integral is the antiderivative, should give us gallons. Well, what happens? You do the antiderivative, and of course, when we do the antiderivative, we leave off the plus C. And think about let's call this V prime in here. So what would be our fundamental theorem part 2? Would be V of 4 minus V of 0. Now let's think about that compared to what we were just doing. So V of 4 would be the gallons that were there at the end. This would be the gallons that were there at the beginning. When I subtract those two, what do I get? The total change in gallons. So when I do a definite integral, again, it's like there's no plus C, which of course there isn't when you do a definite integral. It's the total change in gallons. Okay? It's the change in the gallons. This does not take into consideration, right, what was there at the beginning. So if you set this up as an integral and said 1,600, you would be making that same mistake. I mean, think about it now. If they would have said if the tank originally has 100 gallons in it, how many gallons are in the tank after 4 hours? You still would have set it up like this, right? You still would have said 0 to 4. And you've got 1,600. What you would have had to have done is said, okay, that's how much additional water came in from 0 to 4. I then have to take that answer and add it on to what was there originally. So either way, you have to consider that original amount, either as an antiderivative problem with a plus C, or now, we've now noticed, this is the first time we've done one like this, as an integral problem. That they're connected, they're basically the same thing. Okay, so, anyway, that's something that we will see. We call that the accumulation function. We talk about the integral now. We're going to start talking about the integral in these story problems as an accumulator. In this case, accumulating gallons of water. It's the amount of change, okay? So whenever we have a rate in here, the integral is going to give us the amount of change that's described by that rate of change. Okay, now, let's go to 2012 free response packet, because number 1 is related to that. Number 1 is very similar. Okay, now we are a few days away from getting into the table problems with a table of values. We're gonna spend a fair amount of time in the next month or so. We'll be getting more into some of these functions of tables, and we'll get much more comfortable dealing with those. But let me just talk through a couple of these things. Use the data in the table to estimate W prime of 12. Now, to me, that should have been pretty easy. What did you do there? That's always great when the teacher says that, right? The teacher says, this should have been really easy. Oh, God, no, I'm not going to answer that. I'm going to get it wrong. Really, right? I mean, teaching 101, that was a dumb thing for me to say. But W prime of 12, what are we looking for? The rate of change or slope at 12. Can you calculate the slope at 12? This is W. So what do? These 2 points right here, right? 12 happens to be right between there. Those are the closest 2 points. This goes all the way back to the beginning of our slope days, right? Pick 2 points as close as you can and do a slope calculation. So when they say show the computations, I mean, this was the actual AP test in 2012, and what they wanted to see on your paper was as simple as this right here. Those numbers written out, 15 minus 9, right? You could use a calculator, so you do the calculation, and then what did it come out? 1 point something? 0.16, so I'll round that to a 7. You could do 6, you could leave it 0.16, remember 3 decimal places. And this would be degrees per minute, right? W on top was degrees, minutes on the bottom. Degrees per minute says use correct units, interpret this meaning. So what would you say? At 12 minutes, very key to get that in there. The temperature is increasing because it's positive at a rate of 1.017 degrees per minute, right? Okay. Again, very important, like I said yesterday, that we go back and we just work on these things from before. Okay, I'll make one more other comment about this one, and then we're going to go on to new stuff today. Right here. Use the data in the table to evaluate this. Now that can be very intimidating to see that, the table, oh my God, I don't know what to do. What you should do is this. Fundamental theorem part 2 says that the equivalent to this is what? W of 20. That's it. It means antiderivative, which would be W, at 20, and antiderivative at 0, and subtract it. Well, what's W of 20? 71. What's W of 0? 55. 71 minus 55. 16 what? Isn't it degrees? 16 degrees. What is the meaning in the context of this problem? the amount of degrees that the water changed in those 20 minutes. It went from 55 degrees. It's, yeah, sometimes we make this too hard. I mean, that's what happened. It went from 55 degrees to 71 degrees in 20 minutes. It raised 16 degrees. That's the amount of change, like we were just talking about from problem 43, right? The amount of change over that time period. W prime is the rate of change of the water temperature. So this integral would be the amount of change in the temperature over those 20 minutes. And there it is. Okay? And then we said you could still do part C and some other things. So, all right. So I wanted to get into that. Now, over the course of, the next week and whatever, we're going to have book assignments to do. Somebody have a gateway test to do. I know she got a lot of things. But we want to get in there and get as much work done as you can in these packets that I assigned, those problems I assigned yesterday as well. Okay, let's move on today to some chapter 5 stuff then. Now that we're past the antiderivative portion of it, the integrals, where we can do the antiderivative, the gateway test, some of you passed. Some of you are going to get that passed here shortly. So, let's be trying to get in and get that taken care of as soon as possible. All right, but what's the next step on this? Well, here's what we've started with. Here's what we've done so far in chapter 5. We started out talking about the definite integral. Okay, we started out talking about the definite integral, which is a piece of area. It's a number answer. Now, we've said early on, we said there are 3 different ways we can do that. One is by geometry. That's one of the first things we did. Okay. Matter of fact, I think it's problem number 3 in this packet. Okay. You get a function like that. We can do all kinds of areas. We got triangles, we got trapezoids, we got half circles, right? So one way to find area is that. Now, what's the limitation of that method? Yeah, not many functions look like this, right? It would be a piecewise. It would be kind of a strange looking thing. And it just doesn't happen very often. You need a lot of lines or circles, and we just don't have many of those types of functions that describe real life situations. So that's fairly limited. Okay, then we did the whole big deal with the area function, fundamental theorem, all that great cool stuff. And we found out that, hey, we can find areas with antiderivatives. We got the fundamental theorem part 2, and that's awesome. I mean, that opens up a whole new world of different areas that we can find under all these different curves. But it's still limited. To what? What? There are functions that don't have antiderivatives. Get your calculators out. This one right here does not have an antiderivative. Sine of x squared. Simple function. Now, while you're getting your calculators out, just to equate this to when we were doing slopes. When we were doing slopes, okay, because I mean let's face it, that's the 2 big things in calculus is the slopes and the areas, right? And there's a real connection here between how we approach these things. Slopes were real easy in Algebra 1. Well, they seem easy now. They might not have been then, but they seem easy now. Slopes were real easy if you had what kind of a graph? A line, right? We have a line. The slope is the same over the whole line. But then we got the calculus. We said, but so that's pretty limiting. It only works on linear functions. So then we said, what about curves? They have steepness. What about the slope there? Well, we said that's the slope of the tangent line. How do we do it? Well, the tangent line only touches 1 point. We can't do slope with only 1 point. Well, yes, we can. We'll pick 2 points really close together. And we learned all these great derivative rules. You loved it, right? First gateway test. Derivatives. And the nice thing about derivatives is we can do the derivative of almost every function out there that we can think of. So we're not very limited there. Now, if we would get some crazy function that we didn't know how to do the derivative of, or think about that table function we just looked at for the water temperature. You might have a function that's just a table of values, or just a graph. Well, guess what? In those cases, you might have to just approximate the derivative, the slope. Okay? So there's a real connection here between these ideas. So the same thing's true here. There are going to be some curves that don't have an antiderivative function, so we can't do fundamental theorem part 2. In those cases, the best we can do is approximate what the area is. Your calculator is programmed to do this. So I put two integrals up here. If you type this in without the 0 and the 1, right? Because that should just give you the antiderivative. So type that in without the 0 and the 1, what do you get? It just spits it back out to you. It's saying, I can't do this. There is no antiderivative that I can do. Star. Now this one, there is an antiderivative. So now type it in with the 0 and the 1. Type them both in. Okay, type one of them in with the 0 and the 1, then type the other one. Because they both have areas. They're both functions. And there's a piece of area between 0 and 1 on both of them. Okay? Now on this bottom one, what's it give you? 1 minus cosine of 1, which is an exact value. Right? It didn't give you a decimal approximation. It gave you an exact value. Because it did the antiderivative. And then it plugged in a 1 and plugged in a 0 and gave you that exact value. What do you get on this one? Get a decimal, don't you? Get a decimal, because your calculator is saying, you know what, I couldn't do an antiderivative on this one, and then plug in a 1 and plug in a 0. So what the calculator did is it approximated the area. And we will learn, kind of, what, not that we will kind of learn it, we will learn a process similar to the process that your calculator is going through to come up with that number. How is the calculator coming up with that area? Well, it's doing an approximation technique. And it's running through a whole bunch of calculations really, really fast, and it's approximating that area. And it's accurate out to like 12 decimal places, or whatever it's set to in the calculator. Okay? So that's what we're going to focus on today, is how do we do these approximation techniques. Now, it does get a little labor intensive as far as writing. Those of you that like to draw pictures, you'll love this because we get to draw some pictures and stuff. Okay? But if you don't, well, suck it up. Suck it up, do your best, okay? Yeah, you signed up for this class. Try to stay positive. I was sensing a little negativity in the other class, but today. But
well, that's just because of the people in here.
well, maybe that's it. So anyway, oh wait, number 4.
I said that.
All right. But here's so here's just a function. All right, here's just a function, and I want to do this area from 1 to 5. Okay, so I want to find this, this area, but I don't know what this function is. Let's say it's a function that doesn't have an antiderivative, so I can't do fundamental theorem part 2. It's not a geometry thing. Well, what I can do is break it up, and we've seen this already. We've talked about trapezoids and rectangles, and way back in the beginning of the year we did that. So what I've done is I've connected these across here, and so what that's given me, let's do that in red. So what that's given me here is, like, here would be a trapezoid. And here would be another trapezoid. And here would be another trapezoid. And I could find the area of these, what, 1, 2, 3, 4 trapezoids, easy enough, right? Because I could find these y values by plugging those into the function, whatever it is, and I could do an area calculation, and it would be a reasonable approximation of that area. And what would be better than these 4 trapezoids? 5 trapezoids, 100 trapezoids, 1,000 trapezoids, right? We've done that. We've done that. We talked about that. Okay? And so you can kind of see, just like 2 points really close together would be a good approximation of slope. What would be better? Make the points closer and closer and closer. Okay. So that's what's going on here. And so we're going to, get into all the specifics of this idea. Now, we're going to do it not just with trapezoids, but we're going to do it with rectangles also. And you'll see why we want to do with trapezoids, why we might want to do it with rectangles, and so forth. They're each going to have their own benefits and reasons we want to do it. All right. Now, a couple of points here. Notice we have 1, 2, 3, 4, 5 points that divide this interval. The interval, I'm using some terminology that you're going to become familiar with here. our interval goes from 1 to 5. There are 5 points that make that interval. And it divides it into what we'll call 4 sub-intervals. Okay? So from 1 to 2, 2 to 3, 3 to 4, 4 to 5, those are called sub-intervals. And so the number of points is always one more than the number of sub-intervals you have. Okay, you have the left edge, then the next, then the next, then the next, then the far right edge. There's always one more points than the number of sub-intervals. Okay, just something that will come up later, and so just kind of hang on to that thought. All right. So some more terminology, and I don't know if you draw this picture or not. It doesn't really matter to me on this in this case, but some more little pieces of terminology here. So in general, kind of what I was just talking about on this last one. So if we have a piece of area from A to B, and we want to divide it up into some subintervals so we can do trapezoids or rectangles, whatever, then we're going to label those subintervals like this. And so since we always have one extra, we're going to start counting at 0. Okay, so we're going to call the left edge x sub 0, and then x sub 1, x sub 2, x sub 3, and the last one would be x sub n. So if we were going to do 4 subintervals, we'd have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So the number of subintervals is always that last number. Okay, 4 subintervals will end at x sub 4. 5 subintervals, we'd end at x sub 5, and so forth. So we'll start counting there with x sub 0. So again, just some terminology that we have. All right. So let's take a look at what these rectangles kind of look like, just to give you a sense of this. So here I have an area, it's kind of shaded in gray, and I'm going to put in there 4 trapezoids. Okay? And like you guys said, if 4 trapezoids are good, look at the area, it's not bad, it's pretty close. The yellow area is pretty close to the actual area right here. Well, if 4 are good, 14 would be better. Look at that, really good. 24 would be even better. 34 would really be good. Right? And now we're accurate out to like 2 decimal places. Now, we certainly don't want to have to hand calculate 34 trapezoids. Okay? We don't really even want to do 4 probably, but you don't get a choice there. Okay? But matter of fact, the rule is going to be this: that if there's less than 10 subdivisions, we will write them out by hand and do hand calculation, like so on our next quiz. You'll still get to use a calculator to help you add and do those things, do the calculation. And if there's 10 or more, then I'm going to give you a little program to put into your calculator that you can have it just do the calculation for you. Okay? So under 10, we'll write them out by hand. Over 10 or more, we'll put them into the calculator. Okay? But for right now, our focus will be on the ones we do by hand. Because that, again, is kind of like learning your multiplication tables. In the beginning, you need to work through that to get a sense of what's going on. Then as you move on, it will help you. Okay, so this one, those are trapezoids. Okay, so that's what 4 trapezoids look like. Again, we did it earlier. You take these 2 points, you connect. Okay, the gray, those are your 4 subdivisions, and so forth. Now let's look at rectangles. Here would be 4 left rectangles. Now it doesn't do nearly as good a job as 4 trapezoids do, right? As far as approximating the area. But what if we had 40 left rectangles? It'd be pretty good, right? Or, I don't know, 30, let's go back. There's 34. Now, it's pretty good. Now, it's not as good as 34 trapezoids was, but, you know, what if we had 1,000,000 left rectangles?
Well, I don't know.
Well, the point is, once you get, because I don't think we could, but if we get to 1,000,000 left rectangles, that would be as good, well, it wouldn't be quite as good. 1,000,000 left rectangles might only be accurate to 14 decimal places, and 1,000,000 trapezoids would take us up to 20 decimal places. Well, who cares once you get up that far, right? The idea is that, yeah, 4 left rectangles probably not going to be a great approximation, but if you have enough of them, left rectangles will do just as good a job as trapezoids will, if you have enough of them. Okay? But that's what a left rectangle is. Now let's... Okay. Oh, thank you. Yeah, it says right there, click on it. Right. So, but those are left rectangles. But now you're going to be drawing this, so let's understand how they did this. So you've got your 4 subdivisions, right? Divided out. We take the left edge, we go up to the curve, and we draw a cross. And then we take the next left edge to the curve and draw a cross. Take the next left edge, right, and draw a cross. All right, that's what left rectangles look like. Let's look at right rectangles. Those are right rectangles. Right rectangles, you take, in your first subdivision, you take the right edge up to the curve, and then you go backwards. Now, somebody in the other class, Lillian, as a matter of fact, which I don't know, I accused him of his thinking is backwards, and so it fit on this one. I don't know. But it actually had a good idea. He said, we're doing right rectangles. He wanted to start at the right edge and go backwards. I said, okay, that's fine. Take the right edge over here and go back. And then take this right edge and go back. Take this right edge and go back. That's fine. I usually think in terms of left to right, but he was thinking that. But the idea is that the right rectangle connects to the curve at the right edge of the subinterval. Okay? And that's for right rectangles. And notice that's a little bit too much. It's a little bit of an overestimate. But if we had enough of them, it would be a good estimate. And then the last one we want to talk about are midpoint rectangles. Midpoint rectangles say, okay, here's your 4 subintervals again. This time we're going to go to the midpoint of the subinterval and go up to the curve from there. And then we'll draw back that way and back that way. Now this doesn't touch the curve. It's close, but that's just coincidence. We're just going to go back to the end of the subinterval. Here's the midpoint of this one. Go up to the curve and then draw like so. Midpoint, go that way. Midpoint, and go that way. Now, there's nothing that says we have to draw our rectangles at the left edge or the right edge or the midpoint. We can pick a point a third of the way in here, go up to the curve, and make a rectangle there. Or we could go 7/8 of the way across. Go up to the curve and make a rectangle there. It wouldn't matter. Okay, but most of the time, 99% of the time, we're going to pick the left edge or the right edge or the midpoint to do. Okay? All right. So that's left, right, midpoint rectangles, and then trapezoids. So we're going to be doing some drawing of those today. Matter of fact, let's start right now. So here's problem number 17. It's part of your homework. I mean, we'll do this one together as part of your homework, and then I think you have another one to do on your own, just like it, as part of your homework. And it's a fairly long problem. It's probably half your homework is doing this one. Okay, almost. Not quite. But almost. Now, remember, mostly we learn about these approximations for problems where we don't know the actual area. But sometimes we'll pick ones where we do know the actual area and we'll compare. Okay, so like on this one, we could actually do this one. As a matter of fact, I think the directions, this is on page 355 is where I'm at. On 355 is where we're at. It says, draw a sketch that illustrates this approximation. It says, draw a sketch that approximates this integral. And they want you to draw L4, R4, M4, and T4. Well, what that means is 4 lefts, 4 rights, 4 midpoints, 4 trapezoids. So we got 4 different drawings we're going to do. I know. Yes. Wrap your mind around it, okay? It takes a little while, but that's okay.
So our homework won't be done if we don't have pictures.
You will have pictures in your homework. Yes, if I go around and don't see pictures, that would be bad. So, if you like drawing, you will love this.
I don't.
Now, yes. Well, okay, this one you're right. Happens to be 0. But, Keaton, I wonder, would it make a difference to you if there was an actual area to find? You'd say, oh, this is much more fun.
Yes.
You're right. I do get it. I'm glad you noticed that. This is x cubed, right? Negative 2 to 2. The area is 0, right? We got some negative, going to cancel out some positive. Absolutely. Not just coincidence. On this one happens to be that. It would look like this, right? We do the antiderivative. You don't have to write this down. But it did say to compare to the actual area. If you can just look at that and know it's 0, I'm fine with that. But then you put in negative 2 and 2. So this would be 16 times the 4th, that's 4. Minus 16 times the 4th is 4. Sure enough, yes, this area is 0. All right. But what if the area is 2? What if the area is 7? Doesn't really matter. The idea is we're going to do some approximations, and we're going to compare them to that area. And they're probably not going to be very good. Let's face it, we're going to do 4 rectangles. It's probably not a very good approximation. We don't worry about whether it's good or not right now. We're just worrying about the process of doing the approximation. All right, so here's what this will look like. So we're going to draw our sketch. That's the first thing it told us to do. So we're going to draw a sketch. You're going to get hopefully good at drawing the x cubed graph here in the next 15 minutes. So something like that. I try not to make it too steep because we are going to want our graphs to fit on here. Okay, something like that. I know 2 would be 8, you know, so my graph's not really the scale very well, but just want to keep it somewhat simple. Now, what does this look like? I'm going to show you how I want you to write this. And I'm going to be kind of picky about it. You got to trust me a little bit. Hopefully I learned that somewhat, maybe not. But if not, just go with it. But I'm not making you do busy work, okay? But we're looking for patterns. And as we go into tomorrow and through next week, you'll see where the patterns are important. So the way I'm having you write it, there is a purpose and there is a method to the madness. All right, so first one they want us to write was L4. Okay? They want us to write out 4 left rectangles. Now they actually want us to draw them first. I think drawing them first is a good idea and then writing out the areas. Okay? So, how do we do a left rectangle? Well, we start at the left edge. Oh, now, I forgot something here. This is important. This is something you should do at the beginning of every one of these problems. We're going to use delta x to represent, delta is the Greek letter delta, the triangle, means change in x. So that's going to be our width. What is the width? If we're going to do 4 rectangles, from -2 to 2, how wide are they each going to be? They're going to be 1 wide. Now here's how you calculate that. Here's a little formula you want to become very familiar with. It's this formula right here. Now let's think about that. B minus A is what? In general, what's B minus A? The interval from A to B. What's B minus A? Don't say area, but the distance between, the total width. There you go. It's the total width of our interval. B minus A is the total width of the interval, and N is how many subintervals. So take our total width divided by the number of subintervals, should give you the width of each subinterval. Make sense? So in this problem, it would be 2, take away -2, divided by our 4 subintervals. 4 divided by 4 is 1. So the first thing you always want to do is calculate how wide are my subintervals. That's nice, it's 1. It would have been a pain if that would have come out like 3/4 or something. You know, then every one has to be 3/4 wide. And sometimes that'll happen, but you know, for now it'll be nice and simple. Each one is just 1 wide. Okay, so we're going to go to the first left edge, which is at -2, and we're going to go down to the curve, and we're going to draw a cross, 1 width, and we're going to go up, and there is 1 left rectangle for that curve. Remember, that's how left rectangles work. We start at the left edge, you go down to the curve, and then you draw across 1 width. Okay, the next one, you'll be at -1, you'll go down to the curve, you'll go across, and that will be your second rectangle. What about the third one? It has, you start at this left edge, you go to the curve, which is right there, and you go across. And so a lot of times we'll kind of draw it in dark, whatever, but the idea is there is no rectangle there. That happens sometimes. If there's no height, so there's no area there. Okay, not a problem. And then the fourth rectangle would be from the 1 up to the curve and then across and so forth. So we have 4 rectangle areas then we're going to add them up. Okay? And we know, of course, the area is supposed to be 0. This is not going to add up to 0, but it usually doesn't come out exact. Okay? Especially when you only have 4. So now, here's where I'm going to get picky about how I would like you to write this. And you'll find it to be helpful as we go through this. So what I want to do is write the area of this first rectangle. Now, how do I get the area? Well, I need the height. How do I get this height? Plug a -2 into this function. We're going to call this function little f. So the way you write the fact that you plug the -2 into the function is you write f of -2. I'm going to insist early on here that you write these in the f notation to begin with, because that helps, especially when the functions get more difficult. Okay? And you're going to get to use your calculators to shortcut this a little bit if you do this. And then I want you to take that times the width, which is, and I want you to write the 1. Now it seems silly. Why would you write times 1? Well, here's why. When you look at this, I want you to see a rectangle. I want you to see that this is a rectangle height times a rectangle width. And when you take a rectangle height times a rectangle width, what do you get? A rectangle area. And right there is a rectangle area. So right there is the first rectangle area. Height times width, height times width, height times width. I want that to be obvious. Okay, what's the next rectangle height? F of -1 times the width plus f of, what's the next rectangle height? F of 0 times 1 plus f of 1 times 1. Notice we didn't use the 2, right? We didn't use the right in, and that's because we didn't need it. We had 4 left edges. That far right edge was not included. Now, the last step would be to then go ahead and add those up. So what's f of -2? Well, you put that into the function now. Now, if it was a more complicated function, -8 times 1 is just -8. It's a more complicated function. We could have defined that. Oh, yeah, thank you. Yeah, I did. I don't know why did I write a 2? Oh, yeah, I said we didn't use the 2. Yeah. Okay, that's a 1. Thank you. So put in -2, you get -8. Put in -1, cube it, that's -1. Put in 0, you get 0. Put in 1, cube it, you get 1. Now that's the area of all 4 of those rectangles. That makes sense. This one's -8, this one's -1, this one's 0, this one's 1. Now, there will come a time here where we won't draw these pictures that much. Our next quiz, yeah, you'll be drawing some pictures. Today's homework, a lot of pictures. Okay? But there will come a time where we will do these approximations where all you'll do is write this. You won't need the picture. And if you think about it, it's not that hard. You're going to say, well, okay, how wide are they? They're each one wide. Where do we start? -2. Okay, so the first one, rectangle height would be -2. The width is 1. So where's the next one going to be? -1. What's the next one? 0. Next one, 1. And you'll be able to write these out without having to have a picture to look at. Now, you can probably do it now. But we want to get used to doing it with the pictures and so forth and get that to sink in. And then this will always make sense to us, hopefully, that rectangle area, adding them up. All right, when you add those up, you get -8. Clearly, that is not close to the actual area, but that happens when we get into these. Okay, we'll pick up the pace here a little bit. We're now going to do R4. So we're going to draw a picture. Okay, so we're going to in here with our x cubed. Okay, so we're going to draw our x cubed graph again, and now we want 4 right rectangles. So how is that different? Start at the, so that'd be -1, or are we going to do like Lily? We like Lily that way? Okay, he'll be excited about that. I'll tell him we guys like that. Okay, so we're going to start back over here. Now, the only thing I would say about that is when we write it out, I think we should write them from left to right. We should write our rectangles from left to right. I don't know that that's a big deal. Actually, it wouldn't be wrong to write them the other way. But I think like our multiple choice and those kind of things, I think they'll usually be written in. Okay, so we're doing a right. This time, this one would be 0. It doesn't seem like that big a deal drawing these, but you'd be surprised how many ways you could all of a sudden get kind of confused and draw something wrong. But this one, because how we get the height of the rectangle is at the end point we're at, we go to where the curve is, and then go across. Well, when we're here, the curve is right there. It's at 0. And so that's why it's nothing. Because there's no place to go to get to the curve. All right? So there are the 4 right rectangles. So if we go from left to right, this would be f of the first height is evaluated at, when I say evaluated, I mean that's what we're plugging it in to the function. It's evaluated at -1. And again, the width is 1. And the next one is evaluated at 0. And the next one is evaluated at 1. And the last one is evaluated at 2. In this case, we didn't use the far left edge, the -2, when we were doing right rectangle. Okay? Now, you're going to see here in a minute why left and right rectangles are useful. They're very easy to write. Midpoint rectangles are harder because we have to find the midpoint. Trapezoids are harder because the area formula in trapezoids is harder. But here's the thing. Midpoint trapezoids are better as far as approximating the area. If you have to do 4 subdivisions, you'd be better off doing midpoint or trapezoid. Actually, it turns out midpoint's more accurate than trapezoid most of the time. But we're not always stuck doing 4. We can do hundreds or thousands. We got machines that will calculate that for us. So in that case, it might be nicer to use left and right because they're easier to write. And that will be the case. All right, anyway, this one comes out to be -1 plus 0 plus 1 plus 8, which is 8. Okay, again, not 0. Yeah, so, average. Actually, it turns out that will be a piece of one of these. We'll see in a minute here. But we get that. All right. Let's go on to midpoint. We're getting there. I think you have, and we're going to do 4 drawings for this one. So I think on your homework you have another problem where you'll have 4 drawings, and then I think you have 6 other problems that have a drawing each, 1 drawing in each of them. So you'll get a number of drawings, but they'll go faster and faster as you get better. Okay, so there's our x cubed graph again. Okay, but now, how do we draw our first midpoint rectangle? Yeah, and then you just find the midpoint of each subinterval. Since they're 1 wide, it would be at 0.5. So you'd go there and down to the function, and then you go across half a width and across here half a width. Since the width is 1, you're going a half this way and a half that way. So with midpoint, you always go a little bit both directions. So there is 1 midpoint rectangle. The next one, you go to the midpoint, and you go across. Go to the midpoint, and you go across. Midpoint. Now what's happening there? Any guesses what the area is in those rectangles? Don't you think they're going to cancel each other out? I don't quite look symmetrical, but they should be. Okay, they should be. All right. But when we write this out then, what was the first rectangle height? Yeah, you could do -3/2 if you want. You can do -1.5. There'll be times where it'll be better to do fractions. Sometimes it'll be better to do decimals. It'll all be about finding patterns, and we'll get into that. Now, it's still 1y, though, right? We still have 4 total width divided by 4 subintervals. So it's still, each one is still a width of 1. So that would be that one. Next one would be -0.5 times 1. Next one would be at +0.5 times 1. And the last one is at 1.5 times 1. Now you notice that between these inputs is a gap of 1, because that's the width. So from -1.5 to -0.5, we go 1, 1, and go 1. Okay? All right, now we have to plug those in. So this is a little more complicated. What's that cube? -3.375, thank you. And this one would be 0.125 negative. And this one would be +0.125. And this one would be +3.375. And sure enough, those would add up to 0. Now, it's kind of a coincidence. This is not, a midpoint will not always be the average between the left and the right. That's kind of that's a coincidence on this one because of the symmetry that happens. Yeah.
In this case, instead of just putting in the division function, we used to use the property that it's an odd function to solve that.
You mean to get it 0?
Yeah, like the negative f of x equals.
Oh, this part. So you could say, okay, f of -1.5, since odd function is equal to the opposite of f of 1.5, and so yes, you could. I mean, it's not going to happen very often, but in this case, you could do that, absolutely. Now, somebody in the art class asked, how much of this are you going to have to show? I would say all of this that I have here. Now, even though you use your calculator to cube those numbers, you know, I want to see, for what we're doing now, I would say, Brenna, to answer your question, no. I would want to see these numbers. Now, I guess as long as you get a couple of them, then you know those are negative. That's fine. I'm not going to know if you typed them in or whatever. But I want to see this. I want to see this because this tells me height times width, height times width, height times width, height times width. 4 rectangle areas. These numbers are the 4 rectangle areas, and then this, of course, is the total. That's important. Okay? Now, when we get into trapezoids, there might be a little more to this. Matter of fact, we'll use our calculators to help us out on this last one a little bit. I'll show you how you can do that. So let's go T4 now. Okay? One more time, and then we'll, I've got a definition for us to write down, and then we'll do the first problem in the homework together. All right, so we do want to draw these graphs fairly carefully, so we can make nice looking pictures. Now, what I'd like you to do this time is in your calculator, define, so on the calculator screen, define, and you just type the word define, or you can go under the menu, and I think it's under actions or choice 1 or something, I don't know, you get define. But you can just type out the word define. Let's define f of x to equal x cubed. Now this would be more handy if it was a more complicated function. Okay? So let's define f of x to equal x cubed. Okay? Now, and then we'll come back to it here in a second. So now let's draw our trapezoid. So how do I draw a trapezoid? Yeah, we need this point, we need this point, we need that point, we need that point, and we need this point. We need all 5 of the points. And we connect them. So this would look like that. Now it's a pretty good approximation, and that's because, remember, anytime you have a curve, if you only take a look at a small piece of it, it looks almost straight. So this straight line here between those 2 dots fits that curve fairly well. Now what about the second trapezoid? What about that trapezoid right there? What is it? It's not a trapezoid, it's a triangle. Well, here's the thing. Here's your trapezoid formula. If one of the bases is not there, it's a triangle. Okay?
Whoa.
Half the base times height. So, we'll still call it, we'll still call it a trapezoid. That's fine. Even though it makes a triangle, so does this one. This one right here makes a triangle. And this one is that. So we can still call them trapezoids. And it'd be all confusing. So now this looks like it's going to be 0 as well. I mean, because of the symmetry we can see there. Now that's not a coincidence. It turns out that a trapezoid is the average of a left and a right. But if you think about it, if I had a curve coming up here like this, here would be the left, here would be the right, and the trapezoid would just be connecting right between. So it is the average. So a trapezoid actually is the average of the left and the right. And so that's why this one's going to come out to be 0. Okay? Come on, Cody.
John's
Yeah.
calculator.
I didn't put it on there. It went up.
Make a note. Call Cody's parents. All right. Okay, trapezoid. So the first trapezoid. What are the two heights? How do I write the two parallel bases?
It's F of.
All right. So if you're tired of writing, that's fine. I don't know. Whatever. You're gonna have to do it on your homework. But if you are tired of writing, type it in your calculator form. Type it just like this, because remember, we just defined f of x to be x cubed. Now, on our quiz, on your homework, yes, I want you to write this out. Okay? And then the height of each of these is still 1. The height, remember, is actually the width. The height of your trapezoid is actually the width, because these are trapezoids tipped up on their edge. Okay? So that's the first trapezoid. And so you can see why, yeah, trapezoids are more accurate for 4 of them or whatever, but they're kind of a pain to write because of all this. Now, we are going to get into showing a shortcut way of writing this as we start to look at these. We'll get into that a little more tomorrow. But this first one, I'm just going to write it out. Okay, there's 3, and then here will be the last trapezoid. Now, you notice that in a trapezoid, you use all of the pieces. I use the left edge. At the beginning, I use -2 and -1 for that first trapezoid. The second trapezoid, I use -1 and 0. I use -1 twice. Well, sure, it's the right edge of this trapezoid, and it's the left edge of this trapezoid. So the ones in the middle here, I use twice. The 2 on the edge, I only use once. The -2, I use once. The 2, I use once. So we'll talk about that tomorrow on how we can maybe reorganize this and maybe shortcut this a little bit. But if you would type that in to your calculator just like that with the f's and everything, if you've already defined the function, then you just get an answer of 0. Now, what I would prefer, to be honest with you, is that you would have done each one of these separately maybe. Because, again, if you're using your calculator, I'm okay with that. But what I want to see is the same thing I told you up here. F notation I want to see, but then I want to see what each one of the rectangles is. So here I'd like to know what each one of these is. It turns out this first one is -4.5. The second one is -0.5. The third one is +0.5. And the last one is +4.5. So I would like to see that line there. So as you type them in, you can just type the first one, hit enter, and type the second one, hit enter, type the third one, hit enter, type the fourth one, hit enter. And then you have them. Okay? And then you can go back and add up the various ones. And so, yes, it does turn out to be 0, which, sorry, Keaton, I know that's somewhat interesting, but, you know, or trivial, I guess is the phrase my high school math teacher used to say. Trivial case. But the area, it was 0 on this, and we actually get that. But in most examples, that would not be the case. We would not get the exact area with only doing 4 subdivisions. But this is how we can draw these. This is how we go. Now, if we have a good understanding of this, then we can get into what happens if we do 100. That's where we'll go into tomorrow. What if we have 10 of them? What if we have 100? We're not going to draw 100, but we'll write them out. And what will that look like? And what will the pattern that we see? happen in there because that'll be important for us to see this pattern because we're not going to write out all 100 of them. All right, so the definition I need for you to write down today. I think I have it in here. That was all number 17. Yeah, yeah, it was.
I don't like
that,
I don't like this either.
would it have been better if I'd have made that 17, 18, 19, and 20? You'd have felt like you did more of those 4 problems if they were all numbered? Yeah, if they were, you say, oh, I did 4 problems. Now I only did 1. Did I tell you that this is a second edition of this book, and it's actually better than it used to be? The first edition of this book was terrible about doing it. Like, for example, on your homework today, your first problems are 1 through 6. In the old book, that was 1 problem and 6 parts. And it drove the class nuts. They hated that. Every problem had like 7 parts. This book's actually better about that. It actually took some of those and subdivided them into separate things. It is funny how the psychology of that works. You know, it feels like you did more if you did 6 problems than if you did 1 problem with 6 parts. All right, here's what we're going to write down. Here's a definition. You're not going to have to memorize this, okay, or be able to, you know, rewrite it on a quiz or anything like that. But it is an important term for what we're doing. It's Riemann sum. It's the last name of George Bernard Riemann. Riemann. German. I think it's a German name. Riemann sum. Now, what we've been doing, most of what we've been doing in that problem were Riemann sums. Okay? Now, and I think, did you notice on one of your packets there was a problem that mentioned Riemann sum. Do a left Riemann sum with 4 subintervals. But that's what we've been doing. But let's talk about what a Riemann sum is. Okay, here's the first sentence. Let the interval AB, I mean, I may ask you questions about a Riemann sum. I'm just not going to ask you to write this word for word, but it's probably worth writing. Let the interval AB be partitioned into n subintervals by n plus 1 points. That's the thing I talked about earlier. It always takes 1 more point than you have subintervals. 4 subintervals, there's 5 points. The left edge, the ones in between the right edge. Okay, always 1 more. So that's the n plus 1. So basically, what we're doing here is taking all this stuff we've been doing today and kind of summarizing it here into a definition. Okay, the next statement says A is equal to x sub 0, which is less than x sub 1, which is less than x sub 2, dot, 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 is less than x sub n, and that's what equals B. Now that's where I was showing you that notation in that picture earlier. We're going to call the left edge x sub 0, that's the A. The left edge is going to be x sub 0, then x sub 1, and then x2, and then x3, dot, 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 all the way out to xn. That's all that's saying. Okay, so again, defining our notation.
What's with the equals?
That just means the x sub 0 is the same as A, and the x sub n is the same as B. And the others are all in between, so that's what less than means. So x sub 0 comes first, then x1, and x2. That's all that means. Just a way of writing it. Okay? It basically, that is, well, let's just go back. Okay. Let delta x sub I, don't be thrown off by the I, but it's important. I'll tell you why it's in there. Let delta x sub I be the width of the ith subinterval. If you haven't learned anything new today, you got to say the word ith, maybe for the first time ever in your life. Let delta x sub I be the width of the ith subinterval. Now here's the thing. I think I said this earlier. 99% of the time, our intervals are going to be equal width intervals. Every rectangle will have the same width. But it wouldn't have to be. We could have one rectangle be kind of wide, the next rectangle be narrow, the next one be wide again, or whatever. We could vary the width of the interval. Why would you do that? I don't know, but the point is you wouldn't have to have them all be the same width. So normally our width will be delta x. But we could have delta x1, delta x2, delta x3. That means you could have a different width for every one. Okay? That's what that sentence is saying. So delta x sub I is the width of each subinterval. Most of the time, they'll all be the same. All right. And then this next thing we talked about a little bit too. Choose any point C sub I in the subinterval. It's like a C1, a C2, a C3, whatever. So what that's saying is in each subinterval, pick a point that you're going to plug into the function to have where your rectangle is going to be. Now we said most of the time, again, I think I said 99% of the time, we'll choose the left edge, or we'll choose the right edge, or we'll choose a midpoint. Trapezoids actually don't count as Riemann sums. Riemann, think R for Riemann, R for rectangle. Riemann sums are about rectangles, not trapezoids or anything else. They're only for rectangles. Okay, but I told you that we'll usually pick the left edge and put that into the function for our rectangle height, or we'll pick the right edge for a rectangle height, or we'll pick the midpoint for a rectangle height, but we wouldn't have to. We could pick something a third of the way or 7/8 of the way, whatever. That's what this is saying. Just choose any point in there and let that be your height, but most of the time we'll pick left, right, or midpoint. All right, so all that stuff, just notation, things we already talked about. So therefore, S sub n, S standing for sum, S sub n is equal to f of c sub I. No, that's not an I, that's a 1, I'm sorry. That's C1. I don't know if those stray marks got in there somewhere. F of C1 times delta X1. Now what's that mean right there? Height times width, which means area, rectangle area, right? This is rectangle height, rectangle width. Multiply height times width, you get area. So this is first rectangle area, plus second rectangle area, plus third rectangle area, plus dot, 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 plus the last rectangle area. That is called a Riemann sum. So, to summarize, right, in common ordinary language, a Riemann sum is adding up a bunch of rectangle areas. R for Riemann, R for rectangle. A Riemann sum is adding up a bunch of rectangle areas. This is just the mathematical notation for how it's going to look. But it's important mathematical notation. You might even see where we're going with it a little bit. We'll get to it tomorrow. I mean, this S stands for sum, but if I kind of stretch that S a little bit,
It's like an integral.
So, so anyway, that's called a Riemann sum. So what we're doing when we do these problems, we are doing Riemann sums. So let's start on your homework, and I will do number 1 with you. Your homework is on page 354, I believe, is where it starts. We're going to do number 1 through 6. That was what I told you about. It's actually 6 drawings, okay, of the same function. One's a left, one's a right, one's a trap, one's a midpoint. Then I think the next 5 and 6, I think they've changed the interval on you or something. We're going to do number 7 and number 10. Now, number 7 and number 10 are the only ones where you won't do drawings. You'll just have to write out the rectangle areas. So you'll write out the F notation like we did. You'll do everything like we did on number 17. You just won't have to draw the picture. You just write out the F notation. See if you can do that without making the picture. And then number 16. And that's the one I told you you'd have to do that would be just like number 17. They give you a different function. That's going to have 4 drawings. So altogether you have 10 drawings. 6 on 1 through 6, and then 4 on number 16.
7 is a different section.
Yeah, I do. All right. So number 1. On number 1, they give you a picture of a function, but they don't tell you what the function is. They just give you the graph. So we'll just have to read the points off of the graph. So we need to draw this somewhat carefully. I think it goes, probably a good idea to maybe plot points on it. Okay, so I maybe need some help myself here. So we got a point down here. Goes through there. something like that. Something like that. So you'll have several variations, 6 different variations of that. I don't know if you lay your paper over your book and trace it or something. But be nice to have it be somewhat neatly drawn. And then number 1, I think, now I would actually do these in reverse order. It doesn't really matter, but number 1 says evaluate the integral from -5 to 5. So we're doing the integral from -5 to 5 of this function f right here, the area. And it says using, what, 5 lefts? I think it says first. And then in B it says to draw it. So we've been kind of doing that the other order. We've been drawing it first. Now I don't think it matters at this point which one you do, but the first thing we ought to calculate is what? Before we start drawing anything. How wide it is, right? The delta x. So if we're going to do 5 rectangles here from -5 to 5, how wide are they going to be? Two, right? Because the total width is 10. So, and you know, again, the little formula is just this. So it'd be 10 divided by 5, which is 2. Okay, but that's, you know, you don't have to write that out. If you do it in your head, that's fine. So it's going to be 2 wide. So the first left will start over here, go 2 across to there. The next left, the next one goes, you know, across to there. So we see a situation where, oh, and then we got one that's 0, right? That one is, the left edge is right there at 0. And then the left edge of this one. So it seems like a pretty simple thing to draw a bunch of rectangles, but actually there, I mean, you know, it takes a little getting used to it. After you do a few, and that's why we do a few, you know, after you do a few, it should be pretty simple. But, you know, sometimes getting it in the right place and the right point and so forth. So pretty much guaranteed the next quiz will have 1 or 2 problems where there's a graph or there's a set of points or there's a function and you have to graph it and you have to draw in some rectangles or some trapezoids. And then, so that's actually part B of this problem. And then part A of this problem is to evaluate it, and that's where we write out the F notation. And so this would be, the first height would be at -5, the left edge. F of -5 down here is my height. It's that Y value times 2. And the next one is at -3 times 2. And the next one is at -1 times 2. And the next one is at 1 times 2. And the last one is at 3 times 2. And then you should write out what each one of those is. I think you could just get them right off the graph. That's -2 times 2 is -4. This one I think has a value of 2. 2 times 2 is 4. The next Y value here is at, what is that, 3? 3 times 2 is 6. The next one was 0. And the last one I think had a value of 1. 1 times 2 is 2. No, -1, isn't it? -1. So, -4 plus 4 would cancel. 6 plus -2, that would be an area or a total of 4. So, we end up with a final answer of 4, and that's what I'd want to see. Okay, so that's what that would look like. That's what number 1 would look like. Now you can see why you wouldn't really need this graph. I mean, if you're doing left edge, you're starting at -5, you're going to width of 2, look what happens. That starts at -5, next one's 2 over from that, next one's 2 over from that, 2 over from that, 2 over from that. So when you get to 7 and 10, that's what you're doing. You only have to write out this part. Don't have to do a picture. All right, so best of luck. All right, good job today. Thank you for staying interested and focused, and I'm sorry it took so long, but that was a lot to get through.